Okay, Assalamualaikum and good morning.
Salam, sir.
Salam, sir.
Now,
Morning.
okay, now it's about 11:11 and on 28th of October 2020, we are going into we are going to continue with our lecture, and we are going into a new topic which is on Fourier series. Okay, so any question on the convolution last week's lecture?
Oh, banyak. Alamak.
Banyak soalan.
Samar saya convolution ni. Pening.
Samar ya.
Boleh lah sikit-sikit. Saya pening je.
Yang soalan yang dua soalan tu boleh buat tak? Convolution. Yang last week.
Tu boleh saya sikit-sikit.
Kalau boleh faham convolution. Dua soalan tu. Yang saya bagi tu. It's basically that hari tu kan saya tunjuk video tu, suka tengok tunjuk video tu macam mana dia punya apa ni kata dia punya animation tu of the convolution.
Oh ya.
So basically that is actually the operation of convolution.
Okay.
Yes. Apa benda bunyi tu? Suara saya putus-putus kan?
Jan. Okey ya.
Okay. So kalau tak faham lagi convolution on Friday lah, after our quiz, then I will explain on the tutorial punya question lagi tu. Those two questions on the convolution. So today we continue with the lecture on the Fourier series first. Okay. Now I'm going to share the slides. So today we're going into the series. We have 55 slides together. So this is actually in textbook. I think is I don't know which chapter. Find on Fourier series. On the slide it says chapter 2, but I think it's chapter 3. I think, because introduction, signal, and operation, chapter 1, chapter 2, convolution, chapter 3, Fourier series, chapter 4 on Fourier transform, chapter 5 is on the Laplace transform. Okay, nanti I betulkan sikit lah the chapter number. So introduction. So at this moment, until today, we are looking at the signal, basically in time domain. So we look at systems where the signals convolve with the H transform results in a Y of t. So we are looking at the time domain, and convolution to do because it requires integration and whatnot. So from this, what I call it, the properties of the convolution, and we can simplify the calculation in the frequency domain. So now we are going to transform the signals into frequency domain so that it is easier for us to detect and to analyze the signal. Okay, so many signals are more convenient to process, analyze, synthesize, or compress in the frequency domain. For example, you can do filtering in the frequency domain. You can do also the time domain, a bit more because it's involved convolution operation, whereas in the frequency domain it involves a simpler operation. Actually, it's involved multiplication. Right? So the signal is actually filtered when you use the filter. So you can say, okay, what is the center frequency, or from which frequency to which frequency that you want to pass, and which frequency to which frequency that you want to block. That is the filter, right? Because we use we do based on the frequency, right? So now we go into the topic of periodic signal synthesis. Okay. This is the history, basically, that Mr. Fourier introduced the idea that we can represent all periodic signals at the sum harmonic series. So that is his idea, how it starts with the Fourier series. Okay? So all the periodic signals, see that you can represent in the summations of the harmonic series. For example, sine and cosine. Right? So you can actually approximate the signal by using sine and cosine. Example. This is actually the example of a periodic function. If x of t is equal to x of t plus capital T, capital T is the period. Then x of t is periodic with the period t. So for example, the square wave. Okay, let's say you have this square wave. So the one cycle is basically from 0 to t naught. From t naught to 2t naught is a second cycle, right? So this is a periodic signal. For this example, is an odd periodic signal. So a periodic square wave is actually a combination, a summation in harmonic. So it started with the fundamental signal, a sine wave. Okay. The second harmonic is a 2f sine wave with a frequency of 2f. Okay. The third harmonic is sine wave, a frequency of 3f, and so on. And fourth harmonic is a sine wave with a frequency of 4f. So on and on, and you can sum it up infinitely to produce a square wave. And so basically that this is really an illustration. This is a fundamental signal, right? This is a fundamental signal, okay? Then this is actually the frequency. Actually, at this f is, let's say we call it at 1, f equal to 1. Then the second harmonic, which is with the frequency of 2f. So in the frequency domain, so this is the signal, right? And when you add the fundamental signal with the second harmonic signal, then you have this function, right? Then you add third harmonic signal, then you get this. So this is the third signal, the frequency spectrum of the third harmonic. And you add the fourth harmonic. So you get this. So the more you add, it becomes closer and closer and closer to the square wave. Yeah? When you add the infinite harmonic, then you get an ideal square wave. Okay, clear? Any questions?
Clear, sir.
So that is the idea that proposed by Mr. Fourier. So from this, that we come up with a Fourier series. So this actually we can show by using the what we call it graphical example. It's other day I can play the video. Actually, it has what we call it this animation.
Oh.
It has an animation. It shows in the what we call it in this box on the right graph. Basically, it draws in the not in the secular form, but in the form of sine wave. Right? So basically, it will draw this 4 sine x over pi, 4 sine 3x over 3 pi, and 4 sine 5x over 5 pi. Right? So that one, let me see. Let me get up from this first. Maybe I can go somewhere. Wait, sorry about this.
Wow.
Boleh?
Boleh sir, boleh.
Boleh sir, boleh sir.
Dia berputar-putar sir.
Yes, saya punya ni tak tahu macam mana, tak dapat.
Oh.
Ya, oh dekat bawah dia ada dekat bawah. Okay.
Oh, ada lagu bos.
Ya,
Okay sir, okay sir.
maybe I you ya. Apa Okay. Okay. Still tak apa ni. Nampak? So basically it draws the harmonic. The blue one is the second one is the 4 sine 3x, which is the third harmonic, and the fourth one is the fifth harmonic. So this is actually when you add. That is when you add those harmonic.
Harmonic ni dia punya amplitude ke apa sir?
Harmonic, dia bukan amplitude. It's actually the periodic. The second harmonic is basically that it doubles the fundamental frequency.
Oh, it doubles.
Third harmonic is basically it triple. Fourth harmonic is kali dengan 4. Right?
Okay, faham.
So, okay.
Harmonic.
Ini baru ada, nampak? Okay. I will share balik. Okay, nampak?
Nampak ke? Nampak.
Okay, this, you see this? The fundamental is F. The fundamental frequency is F, which is at here is you plot on the frequency domain is at this F equal to 1 F. Second harmonic is basically that it doubles the frequency.
Oh.
So 2F. Third harmonic is 3F. So it's not the amplitude, it's the frequency. Okay.
Okay.
So this one, okay. This tu nampak. Right. So that this one actually it draws the what we call it main frequency, third harmonic and fifth harmonic in this example.
Third harmonic, fifth.
Okay. So that is the now this example is that it draws the summation of first harmonic, third harmonic, fifth harmonic, and seventh harmonic. Dia campur sekali lagi. Another one, 7. So this is the summation. Just now, yang tadi,
Tu
is actually,
summation ke synthesize?
summation.
Oh, summation. Okay.
Summation is synthesized lah, this one.
Oh, okay.
Basically, it creates a new, what do you call it? A new graph by adding, by summing up those harmonics. Summation of the first 4 harmonics.
4.
Right.
So 3.
So this is the first one. This is actually, it draws harmonic individually. So that's why it starts from the origin in the middle, 0. Right? And then the second one, this one basically that it draws on top of the addition. You see this? The center of the second circle is on this parameter. On the third parameter is on this, and the third circle, and the fourth circle is on that. So it's addition. So this is by finite sums of harmonics. This is by finite. Basically, that it takes how many harmonics that you want. This is the first 4 harmonics. Right? This is a periodic sawtooth. How you create a sawtooth.
Tu dia. Yeah.
So this is actually, it draws the individual harmonic, individual signal.
Ni dia buat full lah, 1, 2, 3, 4. First.
Yes. All these 1, 2, 3, 4. Then it draws this, sum it up. And it becomes a sawtooth. One, because use 4 harmonic, 1, 2, 3, 4, 5 harmonic. So the shape is not that smooth. You add more and more, you'll have an ideal shape of sawtooth. The more you add, the smoother the curve becomes. Right? So that is the idea of periodic signal. From there, then we have a series. Fourier series is a method to represent a periodic signal as an infinite sum of sinusoidal wave components. So it can be expressed in the following 2 terms: trigonometric Fourier series and exponential Fourier. We use trigonometric Fourier series basically that you express the Fourier series in the form of sine and cosine. Whereas for the exponential Fourier series, we use the exponential term, e to the power of something. Okay? This is the trigonometric Fourier series. periodic signal, right, with period t may in general be represented as a finite sum x of t equal to 1 to a naught plus a1 cosine t plus a2 cosine 2 omega t and so on, plus b sine omega b1 omega t plus b2 sine 2 omega t. So basically that this is the first harmonic. This is actually the fundamental frequency. This is the second harmonic. Okay, this is the DC terms. A naught is the DC terms, and which this equation can be simplified in these terms. 1 over 2 A naught is the DC term. Then you have the cosine terms. An cosine n omega t, where n is from 1 to infinity, plus Bn sine n omega t, where n equal to 1 to infinity. So this is the trigonometric Fourier series. Here, the trigonometric Fourier series coefficient are expressed by this. An equal to 2t over ratio over t, x of t cosine n omega t dt. Tn is 2 over t, integration over t, x of t sine n omega t dt. This for n equal to for an is actually for n from 0 to whatever. Where n equal to 0 gives the t value. So n equal to 0 basically gives this term. And the rest, n equal to 1, give the fundamental frequency. So this is the fundamental. And for sine, for Bn, n is start from 1 to 2. There is no B naught. Okay. So fundamental n equal to 1, the fundamental frequency, which is also known as the first harmonic. First harmonic is basically the fundamental frequency. So normally I don't say first harmonic, I say fundamental frequency. So fundamental frequency of first harmonic is same thing. Okay. Don't get confused. So example trigonometric Fourier series. The first one is square wave. Find the coefficients of a trigonometric Fourier series for the periodic rectangular path train x of this period of t, path duration of tau, baseline at 0, and path width, path height of v naught. Then write the first 5 terms in x of t. So basically that you need to write the trigonometric Fourier series for this graph. So basically that you have the amplitude of v naught and what we call it period equal to tau. Equal to a period of t, but the path duration is equal to tau. So this path is actually tau. It's because it's from minus t over tau minus tau over 2 up to tau over 2. Okay. So this is actually tau. So that's the path duration of tau. But the period is basically that you have this part and also this part, t. So you need to write this in terms of in the form of trigonometric series. So you have that. So from the formula, you have T naught equal to 2 over t, and the integration from minus tau over 2 to tau over 2. because and x of t cosine 0 t. Why 0? Because n omega t is equal to 0 because n is 0. Here is right. Okay. So what is vt? Is what is xt? Xt is v naught. Basically that you integrate this part because this part is the integration is 0. Okay. So you get 2 over t integration of minus tau over 2 to tau over 2 v naught dt. So therefore, you get 2 v naught tau over t. Do you know how to do this integration? Or first, do you know why you get this?
Formula. Because the first harmony.
Okay. It actually comes from this. Okay. Here.
Yeah.
And this actually integration over the period t. So an, so a0, basically n is 0, so cosine 0, right? And this over this period t is because of actually this period of t. So basically that you have the integration. This is the first part of the integration. This second part of the integration, and this is the third part of the integration. But this part and this part is equal to 0. So you only have this part because x of t is non-zero for this part. So that's why you only have this. If not, to right, actually you have 3 components from minus tau over 2, from here, from tau, from minus tau to minus tau over 2, one integration, plus this term, and plus integration from tau over 2 to tau, right? And from here, you get this. So this one to here to this, I think you know. You have learned that in calculus. So this is A naught. Right? So you get half A naught is equal to V naught over 2. This is the A naught. Half A naught. V naught. Then you need to find the terms for the others. For AN equal to T2 over T integration over T of xt cosine nwt n omega t dt. So you have to find this. So this you can set up the equations like this. Okay, and you get this. This term. Finally, you get so you just substitute n later to find the how many terms that you need. If it's you need what do you call it 4 terms, then up to n equal to 4. So from n equal to 1, 2, 3, and right? For Bn, this is actually, if you look at the signal, this is the odd or even. This is even or odd signal.
Even.
So if it's even signal, therefore, if xt is even and sine is odd function, therefore it becomes 0. Right? Therefore, the integral becomes 0. So therefore, you don't have the coefficient for Bn. N is all 0. Okay? So you only have A0, A1, A2 up to infinity. So this is actually that you need to know the operation of on even and odd functions. The product of two even function is an even function. The product of two odd function becomes even function. The product of even function and odd function will become odd function. So the integral of even function is the twice of the integral form of 0 to a. And the integral of odd function becomes 0 from minus a to positive a is 0, right? So this, right? So that's why just now x of t is even function, but the sign is an odd function. So therefore the integration, therefore the product of odd and even function is an odd function. So when you take the integration of the odd function, you get 0. Right?
So macam mana kita nak tahu dia even function ke odd function?
That one is from last week lecture. Even function and odd function. Right? You compare. Actually, the even function and odd function. You look at the y-axis. If it's mirror image and flick, is an odd function. If just a mirror image, is an even function. You take the sine and cosine, try compare. This one. This is actually, if you take, okay, take the mirror image. So the positive side and the negative side is mirror image, right? Right? So it's an odd, it's an even function. Okay?
Paham.
If it's an odd function, basically that you take the mirror image and you flip the other side. So f of t is equal to f of what? What?
Even.
Apa tu Isan? Apa tu?
Tinggal. Macam tu ke? F of t is equal to minus f of minus t, right?
Yes.
That is an odd function. This one is this curve is f of t is equal to f of minus
Negative
t, right?
Oh.
This is an even function.
Yes,
You see?
even.
You see the value here, f of tau over 2 is equal to the value of f of minus tau over 2.
Yes.
So this is an even function. But odd function,
Odd function.
dia akan kat bawah ni.
Yang mana tu?
Macam sine wave lah.
Oh.
Nanti kejap kita tengok, okay?
Beres.
So that is the even function.
Even function.
So we continue. Therefore, for x of t, you have 1 over 2 a naught plus summation of n minus 1 to the infinity of a n cosine omega n omega t plus n minus 1 summation of n minus 1 to infinity of bn sine n omega t. And since this is actually an even function, therefore
General formula.
this is goes to 0. So you have this. So just now we calculate a naught, half a naught is this, and this part is this. And this can be written as V naught over 2, 2 V naught over pi, and sine pi 2 cosine omega t plus half sine 2 pi over 2 cosine 2 omega t plus 1 over 3 sine 3 pi over 2 cosine 3 omega t. Because we want 5 terms, so we write up to the 5 omega.
Fifth. Oh.
So this is the answer.
So complex, sir. So complex.
Not that complex if you
Sorry.
understand.
Sir, sekali lagi sir, kenapa yang Bn sin n omega t ni jadi kosong sir? Sebab dia bukan odd lah.
No, sebab this because it's an odd function. Even
function. So-
multiply by odd becomes odd.
Odd. Okay.
So integration of odd function is 0. Integration of a
0. Okay.
odd
Okay.
function.
Okay. Faham.
Okay. Nanti kita go through the tutorial.
Alright.
So now another exercise. Find the trigonometric Fourier coefficient for 1 kilohertz square wave with a peak-to-peak voltage spanning -1 to 1 volt, 0 duty value, and 50% duty cycle. Use the time origin so that the series contains cosine terms only. And another one is that to have only sine terms. Okay, how are you going to solve this? Okay, this is for cosine terms only. Remember, if you want to have cosine terms only, therefore the sine form, the sine terms, the Bn must be equal to 0. So how to do that?
Odd
It
function.
has to be an even function.
Oh
It
my
has to
God.
be an even function. So this is the signal, the shape of the signal. So it's centered at 0, time equal to 0, and this shape. So from here, you will only have a cosine function. What about if you want to have a sine function, sine terms only? Which one needs to be 0?
A.
So
An.
an needs to be 0, right? So cosine is what is cosine? Cosine is a odd or even function.
Odd.
No.
Even.
Cosine is an even function.
Yes.
Because cosine of 0 is 1, right?
Yes.
So cosine is an even function. So if cosine is an even function, therefore x of t must be
Even.
to make it 0. If
Even.
cosine is even,
Okay.
to 0 is you need an odd function, because odd multiplied by even, you have an odd function. So therefore the
Okay.
integration of odd function is 0.
0.
So that's why in the if you want to have a sine terms, for this example, the wave you should shift the wave to be an odd function. So there is an odd function. See? This is an odd function. Because if you flip, if you do the mirror image and with a minus sign, you get this shape, this part. This part is actually it's mirror image and flip. Mirror image, if mirror image is here, so that will be a even function. So you minus the sign, so it move here. This become an odd function. So when odd function, when this is even function and xt, now this is odd function, therefore an becomes 0. You live with the sign terms only. So that is what requires for this question. In order to answer this question, that you need to shift the signal, the x of t. So if you want to have a cosine terms only, so like this, you have to have x of t to be even function. So an is equal to 2 over t x of t cosine n omega t dt, and you go through your integration, then you get this 4 over n pi of sine n pi over 2 for n is greater than 0, right? So you get this is for cosine terms. For sine terms only, so this part drops to 0, so you have this only this term. So you do the bn equal to 2 integration over the period t, x of t sine n omega t, and you go through the integration, then you got this answer. So that is the Fourier series for this what do you call it, x of t. Right? That is in the form of trigonometric Fourier series. The second form of Fourier series is exponential Fourier series. So exponential Fourier series, you write the series in terms of e exponential term, e, j, and omega naught of t, or omega n of t. Omega naught of t lah, because n omega naught, n is here. So omega naught is the what do you call it? When n equal to 0 is a DC signal. Where the exponential Fourier coefficient x of n is equal to 1 over t integration over the period t, x of e minus j 2 pi nt over capital dt. So n equal to 0 give the DC signal. N equal to 0, basically that this exponential term is 1, drop. So you have the integration, basically x naught is equal to 1 over t dt, because this term drop out. So you get DC signal. And n equal to 1 give the fundamental frequency or the first harmonic. Okay? Same example or similar example, right? Just now. So we have a rectangular pulse train. Find the exponential Fourier coefficient of a periodic rectangular pulse train with period t and pulse width of tau, as shown below. Right? The previous example was V naught. One of V naught is 1 lah. So from minus tau over 2 up to tau over 2. So basically this is minus tau over 2 here. This is tau over 2. Right? So now you have to find the exponential Fourier series for this function. So this is the solution. So x of n is equal to 1 over t integration from minus tau over 2 to tau over 2, x of t e to the minus j 2 pi n t over t. So you go through the integration, right? So you get this, and you, right? And you use, actually, for this part, you use Euler formula. It can be written as this. 1 over pi n sine pi n tau over t. So basically that you need to brush up on for you to do the Fourier series. Okay? Yeah.
Okay, sir. Okay. Okay, sir. Inshallah.
Okay.
Sir, boleh sir.
So another example. Exponential Fourier series. You have triangular path train. Find the exponential Fourier coefficient of a periodic triangular path train with period t. The base of the triangle is tau and the height is 1, as shown below. Okay? So this is the one side from here to here. So basically after that it repeats. So this is tau. So basically that this point is tau over minus tau over 2. This is tau over 2. Your integration will be from here to here, because integration, this part is 0, this part is 0. So this function, this curve, basically this part is this, and part is actually this. Right? That's where it's 0. So in your integration, we are going to use this equation inside of your integration. Inside here is x of t. Right? So x of n is basically that you have the 1 over t integration of the negative side, which is from minus tau over 2 to 0, of 1 plus 2 over tau t e by n t over capital T t dt. So this part A is actually this, the integration of this part, this. And the integration of this part is this part. This. Right? So you solve for this part. This is how you do it. To use variable substitution, you assign u as 1 plus 2 over tau t. So therefore dv is equal to this. So du is equal to 2 over tau dt, and v is equal to j capital T over 2 pi n e minus j 2 pi n over t capital T t. So you use the substitution, and you do the integration, so you get this part. Get this. I'm not going to go through the integration with you. This one you should study on your own. So you have to make sure that you do revision on your calculus. Right?
Okay, sir.
Okay. So this part is solved. Now we go the second part. For second part, same thing. We do the variable substitution. Then you do the integration. This. Right? So now you add both. And you use the Euler formula. And you substitute this part with this. So you get 2t over tau pi n square sine square pi n tau over 2t. So that is the answer for xn. And how many terms that you want is depending on how changing this. If it's one, if it's two term, then basically N1 and N2. Okay. So therefore, for N not equal to 0, so this is the term. For N equal to 0 is tau over 2T. So this is the answer, the final answer.
Oh, okay.
So that is the final answer for the Fourier series for the triangle wave. Yeah. This what do you call it, graph can be represented by clear.
Yes, sir. InsyaAllah.
Okay. So this actually you need to brush up your calculus.
Baik, sir.
So we have covered the Fourier series on trigonometric Fourier series and exponential Fourier series. Pulse and frequencies is the final part on the Fourier. So this is an example for rectangular pulse. Okay. So let's say you have this rectangular pulse, right? And this rectangular pulse is represented by this Fourier series. X of n is sine pi n tau over t over n tau. For n is not equal to 0, and for n to 0 is tau over t. Right? The time t in this example is 1 second, and the frequency difference between spectrum is actually 1 over t is 1 hertz. So one point to another is of 1 hertz, because that is actually the frequency of the signal. Right? So x of t actually that given this when you do the what we call it, the Fourier, the exponential Fourier transform, right? X of t is actually the summation of, remember, x of t is summation of xn ej and omega naught t, where x, right? So basically that this function, if you want to write x of t, then you have to use the summation of e to minus whatever, right? So you have to kembangkan this one. You have to expand. So we have done, for example, if you have this rectangular path, if you do the series, you get xn of this. So you use xn of this in the formula of for xt. So you get this, actually this series. So I'm not going to go through the process. That one you can do it on your own. You can prove that you get this. And basically that you can plot this. So if you get at this is actually at the, okay, this one is at the n is, what is n? That one is n Let's see, kita tengok kat sini. N positif. Okay. This one is N equal to 5. So, which one? This is here. Okay, this one. And is actually this term. Okay? Minus 3 is 1. Okay? Is actually N 1. 1. Actually this one. This term. 1/2 actually at this. DC is this 0. Right? This one and this is this one. And this actually, okay? So you can recognize this is actually you can plot on the frequency domain. Right? So this is actually the amplitude. This, the height of this. Right? Clear?
Yeah.
So the square wave,
Yes, sir.
the rectangular wave, actually, when you plot in this on the frequency domain, so you get something like this. So you get something like this, right? Which is like a string function, right? From last lecture. So this is actually at the, this is the fundamental, this is the AC, and this is the DC. This is the fundamental frequency, and all the harmonics. And this. Okay. So when you draw, basically, this is in the frequency. This is in time domain. For tau equal to 0.2. Right? So the, what do you call it? If you look at the broader, the width of tau, the narrower the width in the frequency domain, right? The spread, right? And this when tau is 0.1, so you see it's spread. Energy actually in the frequency domain spread wider. So if you have a continuous signal like sine wave or cosine wave, basically that you only have a path at the in the frequency domain. So we have learned that Fourier series is used to transform a periodic continuous time signal in time domain into discrete frequency spectrum. How about a non-periodic continuous signals? Just now we look at the periodic signals. What about if the signal is non-periodic in time domain? What happens? This is a periodic signal. This is t equal to 4 millisecond. So therefore, the frequency is 200 because 1 over t. This t equal to 8 millisecond. Because the, what do you call it, the period is bigger. So, domain. delta f is 1, 2, 5, right? So as the period t increase, the spectral line move closer to each other. Right? At t approaching infinity, basically that when t approaching infinity, it means that the signal is non-periodic. So therefore, the frequency spectrum becomes continuous. Transformation of non-periodic signal to continuous frequency spectrum is called a Fourier transform. So from Fourier series study, we are going into Fourier transform. Okay. So basically, when the signal, when the period is getting larger and larger, the frequency spectrum becomes continuous. So this is at t equal to 16 millisecond. So still discrete. But when t is getting larger, then it becomes closer to the what we call it continuous signal. So you see this, the spacing between the value is at 62.5 hertz, but when t is greater, the spacing only 2.5 2.5 hertz. So if you put t is, let's say, 4,000 millisecond, then it's basically 0.25 hertz. You increase again. Then at the end of the day, that you have actually the spacing of the frequency is almost zero. So it becomes continuous in frequency domain. So that is what we call then we can use a Fourier transform. So this is the summary for trigonometric Fourier series that is written in the form of x of t is written in form of half a naught, which is the DC component, and you have the cosine terms and you have the sine terms. Right? For odd function, basically that the cosine terms drop out. For even function, the sine terms drop out because of the Bn equal to 0. So An is given by this formula, and Bn is given by this formula. And this is the rules. The product of two even function is an even function. The product of odd even function, the product of even and odd function becomes odd function, and the integral of odd function is 0, and the integral of even function is twice.
Sir,
Yes.
saya nak tanya, kalau kita dapat soalan trigonometric Fourier series ni kan, kita boleh pilih either nak buat even ataupun odd. Maksudnya nak pilih cos ataupun sin, ataupun kita kena buat dua-dua sekali?
Tak boleh pilih, because when you are given, you know already which part, whether it will be an odd, whether the cosine terms drop out or the sine terms will drop out. It depends on your signal.
Oh.
So it depends on graph lah kan?
Yes, it depends on the function.
Kalau graph tu boleh buat dua-dua? Odd dengan even?
That one you have to do the shifting. If the question asks you to shift, like the example just now. Yang tadi example tadi, basically the question asks you, what do you need
cosine
to do
only
in order to have cosine only? So basically that is for you to give an understanding. I want to have a cosine term only, therefore the sine term must be 0. What do I need to do in order for Bn to be 0. Bn to be
Yeah.
0 is basically that you
Even.
need to have x of t be an even function.
Yes.
So you make the signal, you shift the signal to be even.
Alright, faham.
If you want to make it the sine only, what it means is that the cosine terms become 0. How to make the cosine terms become 0? An must become
XT
0.
must be
Yes, so xt must be odd function, because odd
Yes.
multiplied by cosine, which is even, is become odd. The integration of the odd function is 0.
Oh, okay.
Okay.
Faham.
So it depending on your x of t. Yes, this function x of t. If you see that the function is odd, therefore you have the terms of the cosine term will drop. Then you have the coefficient of Bn only. If you see that the function is even, therefore Bn is 0, then you have the An non-zero.
Only. Yeah.
Yes. Right?
Alright, sir.
So that is the Fourier series. Any question? So basically, that is on the Fourier series. The next one is the basis actually on the Fourier transform. Fourier transform. You can see the slides on Fourier transform. I just want to show a bit. After that, we can finish class for today. Okay, this is the properties of Fourier transform. Fourier transform is that when you have a non-periodic signal, when you have from infinity to infinity. So this is the properties of Fourier transform. This is the definition of Fourier transform. We have a signal x of t is equal to integration of minus infinity to infinity of capital X f e by f t df. So in frequency domain, x of f is equal to this. So basically, this is really when you want to do a inverse Fourier transform and Fourier transform. Let's say from time domain, you go to frequency domain, you use the Fourier transform. If you want to go, if you want to have from frequency domain to time domain, then you inverse frequency domain, frequency transform. Okay? There is the definition. The first property is the linearity properties. Linearity property says that if in the time domain you have axt plus y of t, in frequency domain, the linearity properties is preserved. So it can be ax of f plus by of f. So this is the linearity properties. The addition, subtraction of a two function time domain is preserved in the frequency domain. Time reversal of minus. When transform into frequency domain, you have capital X minus F. So the time reversal is also preserved in the frequency domain. The duality, capital X of t is X of minus F. The time shifting, you shift by a delay of by t naught in in time domain, frequency domain, you have x of f e to the minus j 2 pi f e naught. You shift in the frequency, then in time domain, x of t e j 2 pi f naught t. That's when you want to do the conversion. And the convolution, remember in the last week's lecture, the convolution as x of t and y of t. So in frequency domain is a multiplication, x of f times y of f. And the differentiation in the time domain, in the frequency domain, basically that you multiply j 2 pi f. Okay, these are the properties of the Fourier transform. Right? So what is the Fourier transform? In the previous lecture, we looked at the Fourier series, which is a periodic signal. So in Fourier transform is for the non-periodic signal. But we can also use for periodic signal. So the Fourier transform is another method for representing signal and system in the frequency domain. So this is the forward form. So x of t, the capital X of f is equal to the Fourier transform of x of t, which is given by integration from minus infinity to infinity, x of t e to the minus j 2 pi f e dt. So this is the formula of Fourier transform. Right? And of course, conversely, this is the inverse Fourier transform. So x of t is equal to inverse Fourier transform of x of t, and is given by this formula. Minus infinity to infinity, x of f e j 2 pi f e. So this is the formula for the Fourier transform. So example, definition of Fourier transform, example of Fourier transform pairs. Find the Fourier transform of this square rectangular wave. The formula is given x of t is equal to v naught for minus tau over 2 up to tau over 2 and 0 elsewhere. So this one, if you want to use Fourier transform, therefore you have to set up the equation. The equation is that x of t, x of f is equal to integration from minus infinity to infinity, x of t 2 pi f t dt. And this one actually you have three components. The first component is 0. The third component is also 0, this one. And you have only this part. So you integrate from minus tau over 2 to tau over 2 of v naught, because of v naught, e minus j 2 pi f t dt. You go through the, what do you call it, the math, you end up with a v naught t thing pi f tau. So this is the of the Fourier transform of the rectangular wave at the rectangular function. Right? Clear?
Okay.
Another example. If you are given a triangular function of x of t is equal to v1 times 1 minus 2 tau times the magnitude of t between minus tau over 2 to tau over 2 and 0 elsewhere, find the Fourier transform for this. You set up same equation. Okay. So this means that this one is actually for this part, and this part is for this part. Okay? And you do the math, so you get this. Right? The calculus, your integration. That one, this is time for you to review your what do you call it, your integration. Right? So these are the short table of Fourier transform. If in time domain is E minus AT UT, therefore the integration is the Fourier transform is 1 over A plus 2J 2 pi F. Okay? If you have the what do you call it, time reverser, you have time reverser minus sign. So this, right? So if you have E minus A amplitude T, this is the Fourier transform. If T E minus AT UT, this is the Fourier transform. So these tables that you need to familiar with. This is actually the impulse. Impulse in time domain, in the frequency domain is equal to 1. If it's impulse in frequency domain, in time domain is equal to 1. So DC will give this. This is actually 1 from minus infinity to infinity. So it's a flat line. So in the frequency domain is a impulse. If it's a cosine, so this is actually number 8. This is actually a shift in the an impulse shift in the frequency domain. A shift in the frequency domain represented by E J 2 pi F naught in the time domain. This is the cosine, this for sine, and this is the Fourier transform for a step function ut. So you have 1/2 delta f plus 1 over j 2 pi f. So these tables that should come handy for you when you want to do the Fourier transform. This also. So you can go through this on your own, right? The tables, right? So these are the Fourier transforms, the properties, the linearity. So if x of t transform into x of f and y of t transform into y of f, then axt plus by of t transform into axf plus by of f. So this is the linearity properties. So linear in time domain transform into also a linear in frequency domain, right? With the same amount of factor coefficient a and b, right? So using the linearity properties, find the Fourier transform of x of t, where x of t is equal to 2 for minus 2 to 2, and x of t equal to minus 1 for between 2 to 4. The magnitude of t is 2 to 4 and 0 as well. So basically, if you draw the graph, it's like this. So this one is basically that this function can be represented by the steps, a summation of steps functions. So let n of t equal to x1 of t minus x2 of t, where x1 of t is 3, add from -2 to 2, and 0 elsewhere, and x2 t is 1 for -4 t to 4, and 0 elsewhere. Right? So basically that is a combination of these two functions. This one function, this is x1 of t, and this is a function of x2 of t, which is given by this formula: 3 rectangular t over 4, and x2 t is actually rectangular of t over 8. So when you use the linearity properties, and Fourier transform pair for rectangular function, so basically that x of f can be written as x1 f minus x2 f. So this is actually from the table. This actually 4 rectangular t over 4 is actually, this is the Fourier transform for that, and rectangular t over 8, this is the Fourier transform for that. So you can add these two functions or subtract, so you get this, and you can simplify, you get this. Okay, clear? So basically that you have to decompose this function into what I call it, two different curves that you can add together, so that you can solve this problem. If not, it's difficult for you to solve this problem unless you decompose the signals into something which is easier to do the Fourier transform, right? So basically that you have to go through this, which function that you can use to do your transform. So basically that you use this, okay? It's a rectangular of t over tau. So you decompose that signal to these two rectangular forms, right? One is 3 rectangular t over tau, which is the first tau is 4, and this is the rectangular t over tau, the tau is 8. So then we use this from this table. Basically t over tau, for tau over 8, basically 8, saying pi f 8. Is 8 saying pi f pi 8f. Okay, this. So you can use the tables, right? But the trick is that how are you going to decompose this function into this function, into recognizable function, right? That's one method. Another one, you can decompose this into step functions. Then step function, basically you have 1, 2, 3, 4, about 5 functions. So if you use step function, basically you can use this. You can use this transform. You can do that also. So it depends on how you decompose the functions in order for you to solve the problems. In this example, they use the rectangular, and this can also use, you can use the step function, the UT. So for if you use UT, basically you have 5 terms, and you have to do some manipulations in order to get the same answer like this. Okay? You get the same answer. That one you can try on your own. Time reversal. If you have x of t transform into x of f, therefore x of minus t transform into x of minus f. So find the Fourier transform of x of t for ut minus ut minus tau over 2. Then use time reversal properties to find Fourier transform of its even and odd parts. Even and odd parts, any function f of t may be represented by the sum of two components such that f of t equal to the even component of t plus the odd component of t, where f of it, the even component is actually ft plus f minus t over 2. For odd component is f of t minus f of minus t over 2. So basically when you add, so this term drop. So you have f of t. Right? So this is actually the solutions. X of t from 0 to t or tau over 2. Basically this 0 to tau over 2 of 1 ej minus 2t dt. Yeah. So when you do this, you get this, right? And this one actually you can decompose into even and odd, right? So this is actually if you use the decomposition into even and odd. First you take the even function, so x of t minus x minus t over 2. So this is your what we call it Fourier transform, and you go through the process, you get this part. So this is actually, see this here. So the even function give that part, and the odd function, and you go through the math. This part actually give this part. So actually this is the transform of the odd of the even function, and this is the transform of the odd function. Right? This actually when you do directly, and this the second part here when you do decomposition into even and odd. This is time frequency duality. Right? So x of t transform into x of f. So capital X of t transform into x minus f. You use the duality properties to find the transform of yt equal to sine of 2 pi f naught t over pi t. So the solution is that y of t sine 2 pi f naught t over pi of t is equal to 2 f naught sine 2 pi f naught t over 2 pi f naught t is equal to 2 f naught sin 2 pi f naught t. So basically you refer to the tables. Number 17. So x of t actually this. So basically that this part you decompose, you get this f of t. This sine of t can be written in this form. And actually this form actually this. You make it into some recognizable form so that you can use these tables. be stable. So actually you recognize this. Tau sinc pi f tau. From there, then actually you know that the transform is x of t rectangular t over tau. So you can use then you can apply the duality. So therefore x capital T of capital XT is equal to tau sin pi tau t. Okay? And this is really x minus f rectangular minus f over tau or rectangular f over tau. So tau is actually 2 f naught. Right? So therefore yt f naught sin 2 pi naught ft is transformed into y of f is rectangular of this. This is the one in between minus f naught to f naught and 0 elsewhere. So this is the time frequency duality. This time shifting. So basically that I stop here because it's you have a lot to digest. Okay. So I'm not going to cover time shifting today because you need to digest on the frequency Fourier series and also Fourier transform. Right? So you have a lot to go through. Right? And I know that some of you forgot your calculus. So I give you time for you to review your calculus. Okay. So I don't want to burden you with additional information for today. Enough. We stop here first. Any question?
No, sir.
No. So basically clear, or everybody asleep already?
No, sir.
Okay, sir.
Yeah.
Baru naik.
Maybe someone sleeping.
So basically, what I'm going to do is that I will check with the schedule whether we are ahead or we are behind, and if we are ahead, then I will do more exercise for you to give you a further understanding. If we are behind, then what I will do is that I give you more work for you to do on your own, to get your understanding on your own. Okay? But in terms of lecture, I will cover everything. The only thing is that whether I use more, I'll give you more examples or less example depending on where we are compared to the others. And I think so far, most probably that maybe we are a bit ahead lah kot. Because what I want to do is that I want to cover all the material on the analog signals before the first test. So I want to cover all the lecture first, then after that we'll go through the exercise and the tutorial to give you a further understanding.
Alright, sir.
Yes.
Okay.
Alright, sir.
So the what call it? I can stop the sharing of the what call it slides for today. Do you have any question
No, sir.
or confused? Or you are in a state of confusion?
Yes, sir. 100%.
Confused.
Confusion, sir.
And
Other nation, sir.
Huh?
In other nation.
in other nation,
Imagination, sir.
Tak dengar, putus-putus.
Imagination, sir.
Imagination.
In the imagination. Yeah.
Tak apa. So just basically next week we'll go through slowly and with more examples. Today I just give you the theory. And what I'll do, just like previous chapter, I give you some questions and we go through one by one. But tomorrow is holiday. So on Friday, we'll do a short quiz and then we'll cover the convolution. You can ask me about the convolution, anything that need clarification. And next week we'll continue with the lecture and we'll do the tutorial after that. On the same week, on the Fourier series and Fourier transforms. Next week we do like that. And maybe most probably that we can cover some Laplace next week also. Okay. Any question?
No, sir.
No. So
No,
basically, stop the lecture, the class today. We can stop here, right? And see you on Friday. So I'm going to stop the
Sir.
recording. Yes.
Friday quiz pukul berapa yang sir?
Friday kita buat pukul 9 ke nak pukul 8?
Sembilan.
Pukul 9. And
Sembilan tu, sembilan.
You have class pukul apa? Friday? Tak ada. Anybody has class?
Ada. Mandai. Tak
Pukul apa?
tahu lah.
Kita buat pukul 9. Siapa ada kelas pukul 10 to 11? 10 to 11. Anybody?
Time tu.
Ada?
Okay. Tak ada time tu.
Tak ada. Then basically we do on Friday from 9 to from 9 before 11 and we stop before 11 lah.
Alright, sir.
So about one hour something. Okay.
Alright,
Okay, sir.
Okay. So next week, on Friday, we'll do our quiz about at 9. Then after that, we continue with some tutorial and clarification on the convolution. Okay. Thank you. Assalamualaikum.
Waalaikumsalam, sir.
Waalaikumsalam, sir. Thank you, sir.
Okay, I'm going to stop the recording.